Hi everyone. So here I present some of the work that we have done in COMET. COMET is a UK Centre for Observation and Modeling of Earthquake Tectonics and Volcanoes using satellite images and the ground measurements to study deformation and geohazards. And much of the work that I'm presenting today has been carried out during the time that I was in Leeds. And but now I'm a COMET scientist at the University of Exeter in Penryn campus, following the same line of research. So the main motivation that we have in COMET is to understand how continents deform over time by tracking the kinematics and dynamics of the continent's deformation to assess the distribution of the seismic hazards. This is the main objective. And our main focus is in the Alpine Himalayan belt, which is a very long area from China to Europe. And in this area, I mean, we have the African, Arabian, and Indian plates, which are colliding with the southern edge of the Eurasian plate. And this is, I mean, tectonically very active region, and more than 75% of earthquakes killing more than 10,000 people in the past century have occurred in this region. So we followed a number of processing steps to achieve this objective. The first part is the InSAR processing. And for this purpose, we used the Sentinel-1 data. The Sentinel-1 data, thanks to its own night imaging capabilities, its systematic acquisition every 6 or 12 days, and also its specific design for InSAR has revolutionized the InSAR processing. For those of you who are not familiar with InSAR, InSAR is a remote sensing technique which actually uses the radar images, capture the radar images from an area. If the area undergoes any deformation for any reason, then in the second acquisition, we capture another radar image, and by calculating the phase difference between the two acquisitions, we can measure how much the surface is displacing with a millimetric accuracy. And so, I mean, all these phase differences are called interferograms. So in order to efficiently process these interferograms, we developed a system in COMET, which is called COMET LIXAR system. This system actually is an automated InSAR processing tool which generates interferograms in a global scale. And I mean, so far, we have processed more than 400,000 Sentinel-1 images and produced more than 2 million interferograms, which cover the whole region. The data are publicly available for to access, actually. So the next step is the InSAR time series analysis. I mean, it is essential to do the time series analysis if you want to study the slow deformation, such as the land subsidence, the tectonic movements, where the amount of displacement is on the order of millimeter per year. And so we need hundreds of these phase measurements over time. And then after after having this stack of interferograms, we can run some inversion techniques, as you see here in this plot, to derive the time series displacements as well as the velocities. By velocity, I mean how much each pixel is changing or is displacing over time in millimeter per year. You can see some examples of the velocities that were generated for one example frame. And then, in the next step, we perform referencing of the InSAR velocities to GNSS data. And this is, I mean, the main idea is to underpin the InSAR velocities and tie them to a kind of unified reference frame. And for this purpose, we compiled around 60,000 velocity points from different studies, from different data sets, most of them from some GNSS ground stations available in this region, and also some leveling data and so on. And in this plot, you can see these, I mean, there are different vectors. These vectors showing the GNSS velocities I mean, these arrows shows the horizontal, actually, motion with respect to the Eurasian fixed reference frame. And these, I mean, those circles also just some of the vertical stations that we had in this area. So in order to reference the InSAR velocities to GNSS, we perform a jointly inversion of the GNSS data and InSAR velocities together. So then we get into this InSAR line of sight velocities in a Eurasian reference frame. This is Eurasian fixed reference frame. And we can see, we can clearly see that the deformation signals around in different areas in a high resolution. But these, velocities are in line of sight. They are not vertical or horizontal. By line of sight, how the satellite is looking at the ground in ascending and descending. So in the next step, we perform the velocity decomposition to decompose these reference velocities into the east-west and also the vertical velocities. And so as you can see in the top plot, this is the eastward velocity. It shows how the continents are moving toward the east. If you look at for example, this area in the west, this is the Anatolian plate, and we can clearly see that the westward movement of the Anatolian plate with respect to the Eurasian plate on the order of 20 millimeters per year. And there are some sharp color changes across the North Anatolian fault and also the East Anatolian fault. Quite clear, and also there are many other interesting features in this area which we explored in many different publications. And before going to the vertical velocities, I would like to mention that as the tectonic plates move, strain is accumulated, and this will end up to earthquakes. So in the next step, we derive the strain maps, which are basically calculated from the gradients of the velocity field. And this color map shows where exactly the strains are accumulated and, more earthquakes. This kind of allows us to pinpoint the areas with a very high resolution and also to see where exactly the strains are accumulated by combination of InSAR and GNSS data. And these maps are used by the impact partners GEM to generate the new models that they use. Now, most of the signals that we see in the tectonic actually features are visible mainly in the horizontal deformation. But the vertical velocity is also interesting. This is most of the signals that you can see in the vertical velocity are mainly dominated by the non-tectonic features, such as the groundwater extraction or the permafrost. These are the two main factors that causes all these features. For example, if you look at these patches, these blue patches in different regions of the study, we can see, for example, in Turkey, in Konya Basin, as a result of the water extraction, you can see a lot of 30, 40 centimeters per year of land subsidence. In Tehran, the same thing. In Tian Shan North and also in Beijing, we can see a huge amount of land subsidence as a result of the water extraction. And another process, as I mentioned, is caused by the thawing of permafrost under the warming climate. And so in this area, for example, in Tibet, we can see a clear special correlation between the subsidence values and also the permafrost zonation index. The high value of this index is highly correlated, which is strongly associated with the permafrost degradation. And this shows that InSAR can be a valuable tool for climate-induced ground instability measurements. So, these InSAR measurements opens up many opportunities for monitoring different type of geohazards, such as landslides, building collapse, volcanoes, and so on. And InSAR's dense temporal coverage and also spatial coverage makes it an ideal tool for anomaly detection in these areas, as well as the pattern recognition. I just present two examples here in the last part of my presentation. One example is about the collapse monitoring using InSAR and machine learning. And so the main objective, this is actually to kind of identify precursory information before a building collapse. And using the InSAR time series analysis and also machine learning techniques. And this is, you can see here an urban region with a few millions of time series points, each have different velocities, and we want to detect anomalous points that may indicate kind of a structural failure. So to do that, we performed a simple but efficient algorithm This is a time series displacement for one point. This black point is the point under investigation. And so we split this area into 3 sections, this time series. The first 2 sections was used for training a neural network model. And then the third section, the rest of the time series actually was used to predict based on the first section. So then after that, we calculate the difference between the predicted time series and also the actual time series. And if the difference is larger than a threshold, this is flagged as a potential hazard, because we can see kind of decline on the time series on that point. And we tested this on a number of points. This is an example which shows a building collapsed in August 2021 due to the nearby excavation. There was some excavation going on here, and the building was collapsed after some time. And when we plot the time series of that point, we can see that after a certain point, this is actually where the excavation started, we can see a decline in the time series displacement of that point. And using this algorithm, we were able to flag this point as a hazard like 2 months before the collapse. And the next example is the algorithm which was developed by my colleague Matt Gaddis at the University of Leeds in Comet. And this is actually for automated detection of volcanic unrest. And so to do that, we also again have the time series of interferograms. We split the time series into a shorter period of 1 to 2 years of baseline stage, and the rest is used for monitoring. And we apply the independent component analysis on the baseline stage to separate the deformation signals from the noise. And the noise here is mainly coming from the atmospheric noises in this case. And then we fit each baseline interferogram as a linear combination of different spatial sources that are estimated here. And finally, we run the monitoring. We apply the same spatial sources which are obtained in the first stage, then to the new interferograms. And if the residuals between the predicted and the actual data grows large, this flags the volcano as having potentially entered a period of unrest. And you can see, for example, from this point, this is flagged, and I mean, the eruption happened by the end of this time series for this specific volcano. And this is actually currently operational in our Comet volcano portal at the University of Leeds. So these are just 2 examples. We can see, I mean, many examples of using machine learnings to find anomalies in the InSAR time series for different applications. So that was my presentation. I just leave it with some conclusions. I'm happy to take any questions.
Thanks, that was great. So I think we've got time for maybe just one question.
Yeah, sure.
But, who's got the one question? I have a question, if no one else has. Okay, yeah, so I was wondering, with this, like the hazard warning systems that you've shown, which look really good, do you have a way of communicating that with like the populations on the ground when you see these things occurring?
Yeah, that's a great question. For the volcanic actually hazard flagging, this is actually operational and is being used by the local communities. And you can show that in Ethiopia, for example, we have a number of volcanoes, and they use this portal to communicate to the people living in the area and just flag it as a hazard and let the people know, make the decision, and so on. I mean, this is being used by different communities which are affected by volcanic unrest.
Yeah, great. Thanks.